I'd just like to say welcome to HAS members and also to visitors from our North of Scotland sister astronomy clubs, Aberdeen Astronomical Society, Caithness Astronomy Group, Murray's Astronomy Club Sigma, and North Ronaldsay Astronomy Group. I know there are 2 or 3 visitors here because a few of them got in touch with me today. I saw Gwen and Fruitsy and Rebecca on, so a very warm welcome to those non-members. Hopefully you'll stick with us after the meeting. Tonight, after my little introduction, we'll have our main talk by Dr. Anthony Luke, followed by questions and answers. Round about 8:30, there will be club news, astro picks and targets for the month, including a very decent comet that is visible very early in the morning, and Gail Hilliard will be doing that for us. And round about 8:45 or just before 9, we'll take club member questions and answers, and that'll take us to the close. Now, there won't be any breaks during the meeting, so if you need a cup of tea or a comfort break, just get up and go. Keep yourself connected to the meeting so you don't have to go through all the palaver of reconnecting when you rejoin. So just a few things about the club regarding finances. Our treasurer, Andy, has successfully negotiated a much improved insurance cover for us. He obtained a quote from another insurance company and he managed to get that to £345 a year. Zurich, our existing provider, have agreed to price match down from their original renewal quote of £515. So that's a saving of £170. And the new policy will cover £3,000 worth of equipment away from the observatory. So great negotiating skills, getting a good result. As I said last month, our financial position is manageable, but we could do with more members being willing to pay their annual subscriptions. Our membership secretary, Gail Hilliard, has recently been getting in touch with people regarding this. Regarding keeping in touch, again, we hope our members have been enjoying emails, Facebook and Instagram links to the various astronomy-related articles and events over the past month. We haven't quite got round to running a Zoom-based club hub yet. That's envisaged to be a wee get-together every so often for club members to have a chat, but hopefully we can have a go over this month as we've got a lot better using Zoom. The observatory, we've been unable to use the observatory since the lockdown, but we've been up there checking it's still okay and in good working order, and it's in good working order. The weather for the last few weeks has been against us attempting to webcast live solar observance sessions, but we're hoping things will improve sometime soon. It is July after all. For your diaries, our next meeting is on Tuesday the 4th of August, and it will again be hosted via Zoom. And as I said last month, our next few speakers have all confirmed they're happy to talk using Zoom webinar, so that'll take us right through and including the September meeting, when hopefully circumstances may have changed. Anyway, that's enough from me about the club. I'm now going to introduce our main speaker for tonight, Dr. Anthony Luke. Anthony is a lecturer in chemistry at our local Inverness College. He's from Middlesbrough and first caught the science bug when he was very young, watching Apollos 15, 16 and 17 on the television. His parents helped him along the way by giving him a small telescope for a birthday present, and he'd look at the craters of the moon for hours. Then his dad came home from the school where he worked with a large refracting telescope which the physics teacher had lent him. That weekend, Anthony and his dad saw the rings of Saturn, the red spot of Jupiter, and best of all, using the sun filter, they watched a display of solar prominences. At school, there were fewer opportunities for astronomy, so his attention turned to chemistry, and he graduated from Newcastle University in 1988, moving just down the road to Durham to do his PhD. He was trying to make magnets which contain no metals. He didn't manage it, but he did make some weird and wonderful new compounds along the way. Anthony's idea of heaven is a huge cupboard full of chemicals, a bench of apparatus, and a PhD supervisor who told him to have some fun and see what comes out. After gaining his PhD, he left academia and went into local government, intending to work only for a year to clear his student debts and then return to university to start research again. 25 years later, having done everything from air pollution monitoring to catching and prosecuting fly tippers, as well as meeting Mrs. Luke, and I'm assuming she wasn't one of the fly tippers, Anthony finally got out and became a chemistry teacher, and here he is today. It's with great pleasure I welcome Anthony tonight, and here he is to talk about the origin of the elements, the Big Bang, stars, and supernovae. Over to you, Anthony.
Thank you very much for a lovely introduction. I'm just going to start sharing my screen. Here we are. Should hopefully be able to see it now. Let's get to the slideshow from the beginning. Yeah, I'm going to be talking about the origin of the chemical elements, about the Big Bang, stars, and supernovae. Let's have a look. This is what we deal with when we do chemistry, the periodic table of the elements, the building blocks of all compounds. Most of the elements in the table are metals, but there are also some non-metals, and there are even some strange ones called metalloids, which have properties of both metals and non-metals. Most elements occur in nature, but some are artificial. But the purpose of the talk is to try and get a handle on where the natural elements come from. Before we answer that question, we need to have a look at some basics of atomic structure. Here's a very, very basic atom, not drawn to scale. We've got a nucleus in the middle, which is made up of protons and neutrons, and we've got electrons orbiting the nucleus. When we talk about chemistry, what we do is we're looking at the nature transformation nature and transformation of matter, making new compounds. And when that happens, we're looking at changes in the distribution of electrons. When electrons are shared or transferred between atoms, that's when new compounds are formed, and there are no changes at all to the nucleus of the atom. But for the formation of the elements, which we're going to look at in this talk, what we're really interested in is the nucleus, where we have the protons and the neutrons. We'll have a look at the properties of these nuclear particles. We've got the proton, which has a mass of 1. That's 1 atomic mass unit, and a charge of +1. It's got a positive charge. And the neutron has the same mass as the proton, mass of 1, and a charge of 0. So it's electrically neutral. And you'll be seeing these color-coded throughout the whole talk. Protons will appear in red, and neutrons will appear as that kind of yellow sandy color. The way that we'll be seeing some of these atoms uses a special kind of notation called nuclide notation. And this is nuclide notation. It consists of 3 parts. The first thing is the atomic symbol. This is the symbol of the element which comes from the periodic table. This is an F, which means it's an atom of fluorine. As a subscript, we have what's called the atomic number. And the atomic number is the number of protons only in the nucleus. As a superscript, we have the mass number. And the mass number is the number of protons plus the number of neutrons in the nucleus. These two are very, very important units. The atomic number, that tells you what the atom actually is. The atoms which are arranged in the periodic table of the elements are arranged in order of increasing atomic number. Each element as you go along in sequence in the table, we're adding 1 more proton into the nucleus. So the atomic number tells us what an atom actually is. In this example here, it's got an atomic number of 9. It has 9 protons in the nucleus. Therefore, it's an atom of fluorine. It can't be anything else. The mass number, on the other hand, tells us how heavy the atom actually is. So it's the number of protons plus the number of neutrons. And if we look above, we can see that protons and neutrons have the same mass. So get used to having a look at these, the way that these atoms are shown using this nuclide notation. when we talk about the building of atoms in the origin of the elements, we're talking about a process called nuclear fusion. That means actually bringing nuclear particles together, sticking them together to make new atoms. We've got protons with a positive charge and neutrons with a zero charge. And in atoms, the nucleus is held together by what is called the strong nuclear force. It's very, very strong, but it operates only over a very, very small distance. And that's the force which binds the nuclear particles together. And if we want to get nuclear particles and stick them together, there is a problem, and it's a very, very big problem to overcome. And that is that when we build atoms, they are built by fusing protons and neutrons together, but primarily we're talking about making new elements, increasing the atomic number. We want to bring protons together, and protons are positively charged, and for nuclear fusion to occur, protons must come together. But like charges, similar charges repel each other. And this means that we've got a huge energy barrier to overcome if we want these protons to stick together. And this energy barrier is known as the Coulomb barrier. And fusion can only occur if the colliding protons have enough energy to overcome the Coulomb barrier. Now, I don't know if anybody can remember back to 1989. This was all over the news. Two chemists working at the University of Utah, Stanley Pons and Martin Fleischmann, claimed to have caused the nuclear deuterium atoms, or what's called heavy hydrogen, to fuse at room temperature. And this was hyped up as being a source of limitless clean energy. But as with all great fairy stories in chemistry, they hadn't managed it. It was not true. Fusion does occur, however, and it occurs naturally. And it occurs naturally in a special kind of nuclear reactor, which provides sufficient energy to overcome what's called the Coulomb repulsion. That's the repulsion between these positively charged protons. And we call such reactors stars. And the reason that stars are perfect places for elements to be built up is because there is enormous heat and enormous pressure within stars. These conditions of ideal these provide ideal conditions for fusion reactions to occur. Let's go back a little bit in time, about 13.7 billion years or wherever it was, immediately after the Big Bang. And immediately after the Big Bang, the universe was too hot for fusion to occur. Things had to cool down a little bit before atoms could start being built. And after about a 10,000th of a second, things had cooled down enough for the first protons and neutrons to form. And then the first galaxies began to, or the first gas clouds, sorry, began to form into what were called proto-galaxies. And then after in the very, very early years of the universe, after about 500 million years or so, parts of these gas clouds became sufficiently dense, and they became so dense that they collapsed into each other, into themselves under their own gravity, and became stars. And the interiors of stars are very, very dense and very, very hot. If we're looking at a density of above 6 grams per cubic centimeter, that's about the same as a reasonably heavy sort of metal, about 6 grams per cubic centimeter. And a cubic centimeter is about the same size as a sugar lump. Got about, and a temperature of about 10 million degrees, nuclear fusion reactions actually started. The first atoms to be produced were, unsurprisingly, the atoms of the very, very lightest element, hydrogen. And they began to fuse together to produce slightly heavier elements, including helium, lithium, and beryllium. Those are elements 2, 3, and 4. Let's just remind ourselves of the principal nuclear particles. We've got protons with a mass of 1 and a charge of +1. and neutrons with a mass of 1 and a charge of 0. But there are also some other curious and interesting nuclear phenomena that we're going to meet. First of all, we've got here the electron. It's got a little sort of lilac purple colored particle with an E in it. Electrons have a mass of 0, essentially a 0 mass, and a charge of -1, so opposite charge to the proton. We have the positron, or the anti-electron, which has the 0 mass, just like an electron, but it has the same charge as a proton. Then we have a neutrino, which has essentially a 0 mass, the same as the electron, but a 0 charge, just like a neutron. And then we also have, finally, a gamma ray, which isn't a particle. It's extremely high energy radiation, very much like X-rays, except even more powerful. So let's have a look at some of these fusion processes that we have. The simplest processes in the coldest stars are what we call the hydrogen burning processes. This is called PP process 1. We've got 2 hydrogen atoms, which will fuse together to produce an atom of what's called heavy hydrogen, or deuterium. It's got a mass of 2, but an atomic number of 1, and it produces a positron and a neutrino. This nucleus of heavy hydrogen can then fuse with a nucleus of single hydrogen, which is a proton, and produce a nucleus of helium. It's called helium-3, but this also produces intense gamma radiation. And then 2 nuclei of helium-3 can fuse to produce helium-4. And helium-4 has 2 protons and 2 neutrons, and it will also produce as byproducts 2 hydrogen atoms. We then move on to what are called the hydrogen burning PP process 2, where we have a nucleus of helium-3 and helium-4 fusing to produce an atom of beryllium. And beryllium is a fairly exotic toxic metal. It's element number 4 in the periodic table. That also produces a gamma ray. This atom of beryllium can then fuse with an electron and produce an atom of element number 3, which is lithium, and a neutrino. This atom of lithium can then fuse with a hydrogen nucleus to produce 2 atoms of helium. And finally, in the coldest stars, we have the hydrogen burning PP process 3, where an atom of beryllium will fuse with a nucleus of hydrogen to produce a nucleus of this element, boron, which is element number 5, and that produces a gamma ray. And boron can produce an atom of beryllium and a positron and a neutrino. And the atom of beryllium will then undergo a collapse to produce atoms of helium. So we're still looking at the very, very lightest elements here. The heaviest one we've seen so far has been element number 5. And at the moment, there are 118 elements in the table, so we've still got a fair way to go. That happens in the coldest stars. Let's bump up the density a little bit. Our sugar lump, our cubic centimeter, now weighs more than 10 kilograms, and the temperature is above 100 million degrees. And at this temperature, helium begins to undergo fusion reactions and larger atoms start to form. These are called the helium burning processes. 2 atoms of helium will fuse to produce an atom of beryllium. An atom of beryllium will then fuse with another atom of helium to produce this atom, which is an atom of carbon. And that's the same carbon which is the basis of all forms of life on Earth. Say we are carbon-based life forms. This is where the carbon comes from. It's produced by helium burning processes in stars. We then go into a very, very complex series of reactions called the carbon, nitrogen, and oxygen cycle. Start off with carbon here, and it will then undergo fusion reactions to produce atoms of nitrogen, N, oxygen, O, fluorine, and even up to here, element number 10, which is the noble gas neon. And the carbon, nitrogen, oxygen cycle becomes very important in stars which are between 10 and 20% more massive than our own sun. Let's get things really dense and really hot now. The core of the star is now so dense that our single sugar lump, our cubic centimeter, now has a mass of 0.5 ton, 500 kilograms, and temperatures exceeding 600 million degrees. And at those toasty warm temperatures, carbon burning starts. And this leads to the formation of even heavier elements. Let's just pause to have a little look at different types of stars. Have a look at something that you may well be familiar with, a Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is like a map of different types of stars. On the horizontal axis, we have the surface temperature of the star in degrees Kelvin, essentially the same as degrees Celsius. And up the side, we have the luminosity, the brightness of the star. Going up diagonally in the Hertzsprung-Russell diagram are the main sequence stars. And these stars spend 90% of their lives just burning hydrogen into helium. They're not particularly hot. And our sun is one of them. Up in the top right-hand corner, we have the giant stars, the red giants, the blue giants. These are nearing the end of their lives. They've used up their hydrogen and they're burning heavier elements. They have a relatively low surface temperature, but a high luminosity. And down here in the bottom left, we have the white dwarfs, very faint and very, very hot stars, very, very small size. These are the last stage of life of low to medium mass stars. They're extremely dense. We can get an idea of the density of white dwarfs by thinking that they have the same mass as our sun, but only the same size as the Earth. So it's extremely dense. So we've had a look at these. We've got stars of increasing density and increasing heat. So we get heavier and heavier elements formed by fusion reactions. The heat and the density, the pressure can push these atomic particles together. It can overcome the Coulomb barrier. So we end up producing atoms from neon to sodium, magnesium, right up to element number 25, which is manganese, until we reach iron. That's element number 26. And at iron, things come to a stop. And the reason they come to a stop is because once you get to iron, the nuclear fusion reactions absorb more energy than they give out. These sorts of reactions are what we call endothermic. They take in heat. Up until iron, these fusion reactions are what are called exothermic. They give out heat. So I'll now have a look at what a star is essentially like once it started producing iron. And if we could slice a star down the middle, we would see that it would be layered a little bit like an onion. We'd have hydrogen and helium in the very, very outer areas. As we start going inwards towards the core, we get heavier elements, carbon and oxygen, then to elements like silicon, until we reach iron. And at the center of the star is a core of iron and neutrons. And if the mass of this iron core exceeds 1.4 times the mass of the sun, and this is known as the Chandrasekhar limit, then the core cannot hold itself together and it collapses in on itself in a fraction of a second. And it collapses in on itself at almost 25% of the speed of light. And this generates an absolutely titanic shock wave which radiates out and blows the star apart. And this is what we call a type 2 supernova. And conditions in a type 2 supernova are absolutely insane. In a supernova, temperatures can exceed 100 billion degrees, 100,000 million degrees. And a single supernova can emit more light than an entire galaxy. And in these immensely energetic conditions, very, very hot, conditions are ideal for the formation of elements heavier than iron. And we can observe these elements in their stars by looking at their spectra from their light. And this is a look at a periodic table of the elements, but instead of the atomic symbols being shown, we've got these patterns of lines, and these are what are called emission spectra. And lines in the emission spectra of elements correspond to movement of electrons between energy levels around the nucleus of the atom. And each element has its own unique spectrum. So each one is a fingerprint. So we can look for these patterns of lines in the light coming from stars, and you can tell what elements are there. Let's have a look at an exploding star of around about 8 or 9 solar masses. It's about between 8 and 9 times bigger than the sun. We can form elements up to and including palladium, element number 46, and silver. Once we get stars of up to 30 plus solar masses, these are called collapsars, and these will produce elements up to and including platinum and gold. I always think that's quite magical, thinking that a star is exploding and it's sending out lumps of platinum and gold out into the universe. So quite a wonderful thought. So here's a wonderful example of a Crab nebula, of a supernova rather, the Crab nebula. It was first observed in the year 1054 in China. And it's a supernova with a neutron star at its center. The neutron star is rotating very rapidly, and the nebula is mainly hydrogen with some oxygen and sulfur. And the exploding or progenitor star is thought to be somewhere between 8 and 11 solar masses. So it'll be producing elements up to about silver. Here's my favorite star when I was growing up, looking at my favorite red giant star in Orion, Betelgeuse or Betelgeuse, depending on how you pronounce it. This is nearing the end of its life. It's a red giant. It's recently starting to dim. Its iron core is on the point of collapse, leading to a supernova. And this had an astronomer being interviewed on the BBC Radio 4 Today program. They actually, somebody had put out a press release saying that Betelgeuse was on the point of exploding and becoming a supernova, and they got somebody on to say, so when's it going to happen? We understand it's imminent. When's it going to be? The answer came sometime within the next 100,000 years, and I don't think that the presenter was particularly pleased. They wanted it to be happening in the next day or so. But within the next 100,000 years or so, I think that Betelgeuse will become a supernova. There it is in Orion. So that is going to be one of these type 2 supernovas, which is going to produce lots and lots of lovely, wonderful, heavy elements. I mentioned about a neutron star, and the neutron star is the collapsed core of a massive star following a supernova explosion. They're extremely dense, and a cube of volume 1 cubic centimeter, about the same as a sugar lump, would have a mass of around about 1 billion or 1,000 million tons. And these are sources of very, very high energy gamma radiation. We call these pulsars. And neutron stars sometimes collide. And when they collide, the amount of energy which is produced is titanic. And colliding neutron stars can provide the energy which is needed to produce heavier elements like mercury, number 80, thallium, 81, and lead, number 82. But if you look, we've still got quite a few elements to go. And in fact, the heaviest occurring natural element is number 92, uranium. So we've still got a little bit to go. What is it that's going to produce enough energy to take us all the way to element number 92? Well, that's when we look at black holes, the collapsed cores of the biggest stars following the supernova explosion. And these are so dense that gravity is so strong that not even light can escape. And there's a supermassive black hole at the center of a spiral galaxy. For example, Sagittarius A star, which is the black hole at the center of the Milky Way, has a mass of around about 4 million times the mass of the sun. And sometimes black holes will collide with each other or will collide with neutron stars. And when black holes are in collision with neutron stars or other black holes, then that will produce the biggest amount of energy, and that will provide the sufficient energy to allow the very, very heaviest elements to occur. It's like radon, thorium, protactinium, and finally number 92, uranium, which is the heaviest naturally occurring element. Here's another example of a supernova. This is a type 1a. This occurs in binary star systems where one of the stars is a white dwarf. The white dwarf is at the center of an accretion disk. It's so dense it will actually pull matter away from the red giant star. And the white dwarf accretes matter from the giant star. It increases in density, its core heats up, and eventually the white dwarf becomes so hot and dense that carbon and oxygen suddenly fuse into heavier elements, and this releases enormous amounts of energy, and we get a supernova. We call that a type 1a supernova. And just like within the type 2 supernova, we have the sufficient amounts of temperature that it will give the nuclear particles sufficient energy to go slamming into each other and overcome this Coulomb barrier, this natural repulsion between protons, so that they will fuse and be held together by the strong nuclear force and create chemical elements. Here's a rather wonderful diagram which has been produced by Jennifer A. Johnson of Ohio State University, showing the different chemical elements and the processes which gave rise to them. See, with hydrogen and helium, we're looking at the fusion reactions following the Big Bang. And eventually we get to the very, very high mass elements, such as thorium, protactinium, and uranium, produced by merging neutron stars. And some super heavy elements like americium and curium, 95 and 96, have actually been detected in stars. And what happens to these atoms? Well, they start reacting and form chemical compounds. And particles of these compounds can condense together to form planets, asteroids, comets, and meteors, and eventually us. Before I conclude this talk, a couple of thank yous. First of all, I'd like to thank my esteemed colleague Jane Manson, who's a lecturer in physics at Inverness College, for teaching me all about emission spectra and some technical advice about nuclear fusion reactions. Being a chemist, all I've tended to be interested in are overlap of and sharing of electrons to make new compounds, but Jane helped me understand some of the strange wonders of nuclear fusion reactions. I'd also like to thank Sigma Astronomy and also Highland Astronomical Society for making this webcast lecture possible, and I'd like to thank you all for listening. I'd be delighted to answer questions now if I'm able to, but I'd also like to send out my email address, anthony.luke.ic@uhi.ac.uk. I'm always delighted to receive emails. Please do send them in, and I promise I'll answer them. And that's all I'd like to say for now. I'd be delighted to answer any questions you might have.
Okay, Anthony, can you hear me?
I can hear you loud and clear, thanks.
Good. I've got a starter question for you.
Okay.
We know that out there in interstellar space, there are not only elements, but also complex organic molecules.
Yes.
When in the cycles that you've described, do you think these complex organic molecules formed?
Well, I think that as soon as the elements are actually formed, once they're formed in space, then they will come together and start reacting. And there's certainly plenty of heat around in the stars for them to start reacting. And we get these, we can see the spectra in the same way that we can see spectra of individual elements. We can also see the spectra of individual chemical compounds, because once compounds start to form, we get chemical bonds, and those bonds will stretch and twist and vibrate, and that absorbs light in the infrared region. So you can use what's called, look at infrared spectroscopy, and you can see these chemical compounds in space, things like hydrogen cyanide, water, and also formaldehyde, which could well be some of the building blocks of life.
Very good. Now, we've got a question from our Eric, and he said that you were describing how the sun has onion layers, in effect.
Yes.
But within each layer, is there some sort of dynamic equilibrium where more or less of each element is being made in a sort of elemental soup, if we can call it that?
Well, I think within each of the layers, there is each one will be a soup, and there'll be lots and lots going on. The thing that will dictate which elements are able to be produced is essentially the heat and the density. It's the heat and the pressure. So that the cooler areas of the sun, which are around near the surface, and when we say it's cool, it's not exactly cool, but it's relatively cool, then there isn't the amount of heat energy or the density to overcome the Coulomb barrier to stick many protons together to make particularly heavy elements. Once you start getting in towards the core of the sun, where it's very, very much hotter and the density is much greater, and there's very much more pressure, then the protons can be squeezed together to produce heavier and heavier elements, and that's why we end up getting the heavier elements building up. But then things do actually stop at iron, because then the nuclear reactions stop giving out more heat than is put in. They become endothermic, and that's why we can only go any further. We can only go further and get the heavier elements if the iron cores of stars exceeding the Chandrasekhar limit explode into type 2 supernovae.
Okay, thank you. Now, there's a question in from one of our distant members, Pat Williams, who's based down in Edinburgh. She says, lithium, beryllium, and boron from cosmic rays. Could you tell us a bit more about these rays in the very early universe?
This is something where I'm not particularly an expert on what cosmic rays are, but I know that the thing about cosmic rays is, as with anything regarding the synthesis of elements, it's a source of energy. Following the Big Bang, there was produced protons and neutrons, and what is needed is sufficient energy to squeeze these things together. And cosmic rays, when they collide with atoms, can give them an enormous. They have such high energies that they can provide localized conditions for smaller nuclei to fuse and overcome the Coulomb barrier. But that's not something I'm particularly expert on. Cosmic rays have always been much more of a mystery to me.
Okie doke. Well, here's another one from myself. I'm now on video as well. We were very fortunate a few years back that we had a lady from the Natural History Museum who came up and told us about meteors and meteorites and such forth, and brought some lovely examples, including the lumps of iron which had the grain structure, the Widenstat patterns and all that kind of thing that had fallen to Earth virtually unscathed because they're so dense. Where did those form? Did they aggregate after the star had exploded, or are they actually a lump of star?
Well, they will be, both things will happen. They will be a lump of star. I mean, when meteorites, iron and nickel, are the two main metals that you find in many meteorites, they are absolutely the fragments of exploding stars. It's the shrapnel caused by an exploding star. It flings out these pieces of iron into the universe, and they go flying through space until they collide with planet Earth.
Yeah, I think that's absolutely fascinating. I mean, these are quite big lumps, I have to say. And to think that that was the origin from a center of a star is just remarkable.
Oh, it is. Very. I mean, it's so easy to get sort of Brian Coxey about it, and just everything it was forged in the heat of a star, but it's true.
Yeah, well, that's impressive. Okay, well, thank you, Anthony. We've run out of questions from the members, so I'm going to hand back to Eric now.
Well, Anthony, I just want to take this opportunity to thank you very much for a most interesting and inspiring talk. I have to say, that was a great question at the end there, Paul. The fact that meteorites are star fragments, that's got me really thinking. Anyway, Anthony, normally you'd be receiving a token of our appreciation and a thank you card designed and printed by Pauline. You will still receive these things, but we'll need to send you either by email or in the post. But Anthony, thank you very much once again. And I'd like to keep contact with you, being a locally based fella now that I know you're there. You could be very useful to our astronomy club, I believe, if that would be okay with you.
Well, if there's anything I can do to help, I'd be delighted to. And as I said, please feel free. Everybody, you've got my email address gone out on the talk. Please don't be a stranger. Send me any questions you have.
Will do, Anthony. Thank you once again.
No problem.
And now to the next bit, our club news, astro picks and targets for the month. Now, Pauline, she's unable to be with us this month, and Gail Hilliard, our newest committee member and membership secretary, has enthusiastically volunteered for the slot, and I'm very much looking forward to it. Gail, over to you.
My name is Gail Hilliard and I'm the new membership secretary. So it's great to sort of hear from quite a few of you now. Thank you so very much for getting your membership fees in. They are greatly appreciated. If I could ask, if you haven't already done so, if you wouldn't mind just returning your membership forms as well. It just gives us an opportunity to collect gift aid where we can. As you know, all of these things really go towards helping the club. And also on that point as well, do tell your friends. It's a great organisation. Known about them for many years. Wonderful stuff, and obviously Anthony's great talk tonight. Hello, Anthony. It's nice to see you, by the way. So please do tell your friends. Membership's only £25 a year, which works out to something like 7 pence a day. So totally worth every single penny of it. Just starting off, I was given this sort of brief by Eric, so I hope I'm doing it the right way. It's the first time I've done this, which is probably perfectly clear that this is all frightfully new to me on this particular format. But I'm just going to start off with the object for the month, and I hope this is what Eric wanted me to talk about here. He sent me details from BBC Sky at Night magazine. There's a fabulous new comment which is just about to it's just visible now from UK. It's around the first magnitude, and I hope you can see the details on the screen here. And it's visible. It's at a very low altitude, which is making it quite difficult, and that obviously combined with the bright skies that we're experiencing at the moment because of the summertime. It's about 1 o'clock in the morning is the best possible time to see it. You have to find somewhere with a very clear view that's facing northeast, and it's currently close to the star Theta Aurigae. Have a look out for it. There's details here on this on this PowerPoint, so we can send that to you. Eric's also done a rather fabulous bingo card as well, so the details are in that too. Have a look round for it, and we'd love to see if you can get photographs. Let us know that you've seen it. Maybe you'll see people out looking for it, but we hope you do let us know you can, because it's tremendously exciting. It's not going to be one of the big glaring, bright, brilliant light up sky ones that was at Halle, but please have a look for it. I think it's quite an interesting thing to see. And I'm just going to show you Eric's lovely bingo card. This is a bingo card that Eric has done. It's I think it's a fairly new idea for the society. As you can see there, right at the top is Comet C 2020 F3 Neowise. have a look at that, see if you can find it, mark it off there and let us know. The other thing that we'd like to look out for this month are sundogs and the circumzenithal arc there. This will be on the website, so you can go have a download that. But if you'd like, we can also perhaps email a copy to you. A copy can be sent to members. We've got your email addresses. So if you would like us to do that, or like me to do that for you, then I can certainly arrange that, because that can go out to you quite easily. But have a look at those and see how well we can do. See who comes first, see who gets the most. That should be quite fun. So there's lots of things to look out for there. Okay, just a little bit of the information. The moon at the moment, we've just had a we've just had a penumbral eclipse on the 5th of July. Not very easy to see because it is the shadow of the Earth crossing the moon. The next one's visible in Scotland on the 30th of November. So as you can see, we've got the third new first quarter and full phases there. The next notable event is probably not that exciting as a sort of events go, but it's a black moon, which means it's the second new moon in a calendar month. So basically it's the antithesis of a blue moon. So they are actually quite rare. They only occur every 32 months. So it's one to put in the diary anyway, just to sort of tick off that you've seen it. And what I've done is slightly different. I'm actually incorporating members' photographs with details of any activities or events. So just going to look at the lunar images. We've got a lovely one here of from Eric, copyright the Astro Highlander. I think that might be sort of his social media handle as well. So that's quite a lovely one there. And then quite a detailed close-up one from another of our committee, which is David Davidson, taken on the 1st of July. So great photograph there, lots of lovely detail. And then onto the planets. That is not, by the way, a photograph that anybody from here has taken. It's a fabulous picture of Neptune. I just love the color. There's not, I would say there's not a tremendously amount of exciting sort of planetary stuff going on at the moment. Obviously the weather is not great. That's not helping, but that's got nothing to do with what you can see celestially. But also it's tremendously bright at the moment. So sort of 1 o'clock in the morning, 1:30 is probably the best time. It's great if you're a sort of a late night person. But Mercury best in the middle of July for early morning. Venus, again, sort of middle of July. Looking quite near the moon, but quite easy to see there. Again, Mars, middle of July. Jupiter, not looking great at the moment, but Dave Davidson did get an absolutely stunning photograph of Jupiter and its moons recently, so that there are opportunities there. Again, Saturn, not tremendously easy to see, but again, another fabulous picture from David. There is Saturn coming up. And again, end of July for Neptune and Uranus. And we've got some members' planetary images now. Lovely image here from Sue Shackleton from North Ronaldsay Astronomy Group, which is the moon rising with Mercury and Venus. And I hope I've got those the right way around. I think I have. Obviously, we've got Mercury here in yellow and then Venus here in red. Lovely photograph with the moon rising there. And again, this is this fabulous photograph of David's of Jupiter. And there's 3 moons here. So it's either going to be one of Ganymede, Europa, Callisto, or Io. And I have to confess, I'm not actually sure which one is which. So apologies there. And perhaps David knows, but I certainly don't. I don't know if there's actually any easy way to tell either. So if somebody does know, let me know, because that would be quite interesting. And again, here's this rather lovely photograph of Saturn, again taken by David on the 11th of June. Stunning photograph here. I think aesthetically just beautiful photograph from Eric of Venus. You can actually see just very faintly around the edges, the atmosphere of Venus there, and obviously in its crescent form as it sits between the Earth and the Sun. Absolutely beautiful, beautiful photograph. Okay, solar activity. We're coming to a new cycle, coming up to a new cycle, as an 11-year cycle of solar activity. It is actually predicted to be the weakest cycle for 200 years, this one. So I think we've got 11 years of not particularly exciting sunspot activity, but then again, that might change. So again, just a little point there, always remember safety first when looking at the sun. Don't use your naked eyes, use a telescope, use a filter when using a telescope, binoculars or cameras. Always make sure you've got a proper filter that's in perfect condition. And that's one of Eric's photographs there, which I sneaked in. This picture I absolutely love. It's by Eric, and it's showing the solar prominences, which are incandescent ionized gases projecting into the corona. The thing that got me into astronomy was actually these. I looked at them when I was about 8 years old in an encyclopedia, and I saw this arc of fire, and it was said it was 10,000 kilometers high, and I was just blown away. I was completely into astronomy from that particular point. So it's a great picture, and it takes me right back to my childhood. Now, just moving on to some other solar images, there's two different types of filters used here. Starting with David Davidson's got a lovely view of a sunspot here, which is AR2765. Now, just going on to that point, AR has two meanings, either active region or autoregressive model. Not sure which they used interchangeably, but I do know that the calculation that they used to get the number is phenomenally complex, and I have no idea why. I thought it would just be sequential, but apparently it's not. David took his photograph with a white light filter, which is essentially a normal sun filter that you would use on the end of a telescope. Absolutely lovely photograph there. Lots of subtle detail, but it's great to be able to see that. The next one is Eric's, which is taken with a hydrogen alpha filter or an H alpha filter, which filters a very narrow bandwidth of light, which is the deep red emitted by hydrogen atoms. I think Eric's picture's been stacked. I'm not sure. I hope he's not offended if I've got that wrong. But it's a stunning photograph. There you can just see the sunspot there very clearly. And then if you move on to the next one, you can see it in so much more detail, much more closely, with all the activity around that sunspot area. Then moving on to 2 days later, just seeing how far that the sunspot has moved across the surface of the sun there, which is quite interesting, how quickly it actually moves, how quickly that sort of, that space moves. So just moving forward now, and I've called this meteorological, which I've actually spelt, goodness me. Is it going to be a sad, sad July for rain? It's going to be rain, rain, and more rain. I'm getting my information from metcheck.com, which I've always found exceptionally good and very accurate. They are saying that it's going to be rain until about the middle of the month. Will be sort of okay for a couple of days, but possibly slightly overcast, and then rain again until the beginning of August, where it starts to brighten up. Just on that point, we've got some really fabulous photographs from members. Beautiful picture again from David Davidson. This is of crepuscular rays. It's lovely. One of my favorite words is actually twilight, and crepuscular is Latin for twilight. I'm really glad that all my years of Latin actually have come in useful tonight. I don't tend to use it very much, and I've forgotten most of it. But basically, it is parallel streaks of light that radiate through breaks in the clouds before and after dusk. They are actually parallel, but because of perspective, it makes them look as if they're radiating from one point. So it's pretty much as if you're looking down a railway track or seeing buildings converging. They are actually parallel. It's a little bit of an optical illusion there. They occur when the sun has set behind irregular shaped clouds, or indeed behind mountain tops, because they tend to sort of just diffract the light. The rays actually are from where the sunlight hits the dust in the atmosphere. And then we've got noctilucent clouds, which are completely beautiful. Again, from Sue Shackleton, another gorgeous picture. This one, Sue's at North Ronalds Astronomy Group. This is taken in mid-June. Absolutely beautiful photograph, lovely colors. So it makes a painting almost in itself. Love it. Again, from the Latin, noctilucent means night shining, and these are night shining clouds, and they're formed by ice crystals in the upper atmosphere. They're best seen from May to August, so prime time to see them at the moment, and always better in the far north, usually when the sun is just below the horizon. So between about 90 minutes to about 2 hours before and after the sunrise and sunset. Beautiful photographic subjects, really interesting, absolutely spectacular. They used to be very rare, and there has been an increase of them in the past few years, and more alarmingly further south. Alarmingly because these are occurring, they think, due to sort of changes in the climate, possibly due to helium being in the upper atmosphere, and that is being potentially worryingly released from permafrost. So as beautiful as they are, they might be a sort of slightly concerning trend, perhaps even a slight understatement there, that there is sort of environmental impact happening here. Some more here, another beautiful picture from David Davidson. Absolutely gorgeous one from Ersan, who's a guest member, or a guest. I hope he'll soon become a member, Ersan. Beautiful image here. It looks like a seascape, just really lovely, particularly around here, just all this lovely sort of brightness in the sky. And I think this is actually a section from a painting here. I think that's the greater picture. And I think looking at this, that's possibly from up near, I can't remember the name. Is it up near New Craigs? I think there's a place up there that you can go because it's overlooking the Keswick Bridge and the Black Isle there. And I think that's Tom Nahurich Cemetery over there. Absolutely stunning picture. And again, another gorgeous one from David of the sun at sunset. Very, very bright, vibrant. And again, another one from David. And from another member, Marion Walker. Again, I'm not quite sure where these are, but beautiful pictures, lovely ones there. And finally, we have a discovery. Scientists have discovered a new kind of black hole that has a gravitational field so intense that no treats or dropped food scraps can escape. And I will leave you on that. Thank you very much.
Excellent. Excellent, Gail. Well, I think we have found ourselves another presenter. That was superb. I really enjoyed that. And you didn't trip up over some of the Latin words I stuck in there. I forgot about your education. That was excellent. Wonderful stuff. We've put the bingo card in. That's it's a mixture of some astronomical objects and some meteorological type objects because it is very light at nights now. But if you download it, or as Gail says, if you contact her, she'll email it to you, and it's worth just having a go and seeing if you can observe these things. Just keeps you active, keeps your eyes going, keeps you looking up at the sky, which is what we want. Now, I've got a little section here if there are any questions and answers from any club members or guest members or visitors. I'm quite happy to try and answer them.
Well, there's none at the moment, I'm afraid, Eric, but we'll just sit here for a couple of minutes, see if anybody comes up with anything. Perhaps people would like to comment on the webinars, these presentations online.
Yeah, if any of the guests who who haven't attended any of our meetings or that, if they want to comment either here or can contact me via Facebook Messenger, that would be really useful for us.
If it would be possible just to put in, as far as I'm concerned, I think you've done a really professional webinar. It's been a pleasure to do. It's been very well organised. I've really enjoyed being part of it, and I think it is very, very professional. I certainly take away a few pointers in terms of the organisation for my online lessons, which I'll be doing next year, which have been somewhat shambolic in comparison. So I think the very, very slick stage management of this has been a real learning experience for me. So thanks.
Good, thanks, Anthony.
Well, I think that we are done. There are no questions and answers coming through, so back to you, Eric.
Okay, well, just thank you very much for taking the time to attend. Hopefully we'll get back together in the flesh, so to speak, sometime soon. But in the meantime, we'll try and keep going with our webinars, with all our social media stuff. We'll definitely try and get some informal chats via webcasting and things over the next month. But thank you very much for attending. I thoroughly enjoyed it myself. I hope you have. See you next time.